महिमा जी आप स्टार्ट करिए।
Okay, sir. Just starting. Knowledge is like a garden. If it is not cultivated, it cannot be harvested. A very good evening, everyone. I am Mahima Dikshit, research scholar. SDPIT Meerut extends a very warm welcome to day 12 of International Training on Precision Agriculture. As we have come so far in the discussion of precision agriculture, today's session's title is Digital Soil Mapping, Use of GIS, RS, and Machine Learning. Today, to share our thoughts and knowledge, we have our eminent speaker, Professor Vikash Sharma, joining us. I would like to take the honor to briefly introduce her with our participants. Professor Vikash Sharma is Head, Division of Soil Science and Agriculture Chemistry at Sher-e Kashmir University of Agricultural Sciences and Technology, Jammu, India. He obtained his doctorate from Punjab Agriculture University, Ludhiana, India, and did his postdoctorate under Raman Fellowship from West Virginia University, USA. He has been a visiting professor at Auburn University, USA. His research interests include digital soil mapping, soil carbon, soil water conservation, land degradation, and soil health. Most of his work pertain to soil in Indian Himalayan region. He has worked on soil erosion risk mitigation, carbon pools, carbon losses from Himalayan soils, and nutrient dynamics in the erosion-prone foothills of Himalayas. He has utilized his experience in remote sensing and GIS and accessing and mapping soil resources in the region. He is presently focusing on utilizing machine learning models in soil mapping. He is also involved in teaching and advising students' research. He has executed multiple projects and is presently the PI of the prestigious NAHE project at SKUAST Jammu. He has over 100 research articles and 30 book chapters to his credit. His latest book is on soils in the Hindu Kush Himalayas. So we are very pleased to have you with us. I would request you to please start the lecture.
Thank you, Mahima. Can you hear me?
Yes, sir, you are audible.
Oh, thank you so much for a wonderful introduction. And I'll straight away go to my presentation. If anybody has any questions, even in the middle of the presentation, I don't mind it. Let's make it a two-way process. So I'll just share my
सिस्टम ऐसा है कि जैसे सर आप अपनी प्रेजेंटेशन को खत्म करेंगे फिर 10 से 15 मिनट हम डाउट क्लियरिंग सेशन रखते हैं, है ना? लोग अपनी क्वेरी को चैट बॉक्स में लिखते हैं और उसको वहीं रिजॉल्व कर दिया जाता है.
Right. Okay, no problem.
Thank you. आप स्टार्ट कर सकते हैं डॉक्टर साहब.
Right. Thank you, Dr. Ankur and Mahima. Good evening, everyone. I'm very pleased to be here with you. And thank you to the organizers for giving me this opportunity. This training is on precision agriculture, and digital soil mapping is an important part of precision agriculture, or you can say smart farming. We are using a lot of words like that. And to be very honest with you, that digital soil mapping is not something very new, and we have been doing it for the last 30 years. But what is changing is the concept in how we are making the soil maps over different time periods. I mean, we started with simple interpolation techniques, then we moved on to kriging and geostatistics, and then we moved on to nowadays we are using machine learning models. So it has been an evolving process like any other science. And the thing is that the evolution is for the betterment and for more accuracy in soil mapping. And when we talk about soils, there's a new term called pedometrics. I hope you might have already heard about it. This pedometrics is about the measurements in soils, both mathematical and statistical. And digital soil mapping is one of the branches under pedometrics that we do. Okay, Let's start with a bit of a background why soil mapping is important and why soil data collection is important. Recently, we celebrated the Soil Day on 5th December this year. And one of the main and the first and foremost objectives of this Soil Day was to map and monitor soil nutrients, apart from maintaining soil health and other functions. So this was in the top of the list. Uh, and another logo you might have seen in the World Soil Day celebration is the Global Soil Partnership. Now, Global Soil Partnership is about coming together and joining all the data sets that are around there and partnering in research globally, because there's a plan to develop a global soil map at a very high resolution scale. And one of the main pillars of this global soil partnership is the information and data collection. Now, once again, this information and data soil collection is already being collected over the last 5 or 6 decades. But as I said, that it's an evolutionary process, and we are adding more and more data as we move on day to day. And this information is all being collected, and then it is being harmonized and standardized in a single format so that it can be used universally. Now, this information and data collection becomes very important because one, it enhances the quantity and quality of the information that we have about the soils around us. And then it helps in analysis and validation of the type of soils that are there. And we can answer questions at both regional and global scales when we have more information. It's just like having any sort of statistics or data that we are collecting, that more the data we are having, and the better will be the what we call the policy that comes out of the data. So coming to pedometrics, the word I used in the beginning of this presentation. So this basically means that it is the application of mathematical and statistical methods for the study of the distribution and genesis of soils. So essentially how the soils properties are distributed. For example, if we talk about, let's say, soil nitrogen or soil organic carbon. So if we are studying that how it is distributed from one place to another place, so that is using pedometrics. I recall my PhD at PAU. My thesis was on potassium, and I studied distribution of potassium and other kinetics and a lot of things. But if you look at the early studies in soil science, there will be a lot of studies talking about distribution of a particular nutrient, potassium, phosphorus, or nitrogen in a particular district or state. So that was sort of a beginning, but in that we used to have only non-spatial data. So we go at a particular location, collect the data, but there was no GPS or no geotagging of the sample. So we had a set of, for example, 100 data points. So it was simply, we used to calculate mean, medium, what is the range of the property, but we could not make it on the maps. So this pedometrics actually tries to work that out, and we use different statistical models. We are using machine learning models to bring about prediction of the soil properties at unknown locations. Unknown locations meaning from where we have not collected any samples, but based upon what we have collected, we can actually predict the samples or the soil properties at unknown locations. So the goal here is to better understand the soil as a phenomena and how it varies in space and time. So when we are making maps, we are not really considering the time, but we are considering only the space in this case. And we use tools like geostatistical statistics, linear modeling, and machine learning models to make these maps. So let's move on to digital soil mapping now. So if you want to define digital soil mapping, it can be said as a sort of a, we can say, if you want the academic definition, then it is the creation and population of spatial soil information. So creation is like we are collecting the data points and we are creating the soils. But population of spatial soil information is done by using the different models, that because when we are collecting samples from any particular given area, the samples are only dot points on that particular spatial uh, polygon. But we have to populate the entire data. So whenever you are looking at a soil map, it is colored everywhere, not just simple points. So that is actually called the population of spatial information. So this is done by the use of field and laboratory observations. This is the primary thing because we cannot ignore, however, technological advancement we are making, but the collection of soil samples still remains the primary task. And how accurately we are collecting those samples will also be defining point for your accuracy of the maps. And this observations that we take for soils and then analyze in the laboratory is then coupled with the spatial and non-spatial soil inference system. So essentially meaning we are making computer assisted maps using mathematical and statistical models by utilizing the soil observations that we are taking in the laboratory. And this is enhanced by the explanatory environmental variables. So the framework of digital soil mapping seems as something like this. It's a combination of soil science, geographic information science, and quantitative methods. So this involves both technological advances and computational advances. So technological advances like global positioning system, remote sensing, field scanners, etc. While the computational advances are like the geographical information systems, digital elevation models, and geostatistical interpolations, among others. However, the basis, as I told you, will always be the soil sampling and the analysis that you carry out in the laboratory. Let's start from the very beginning. We'll start with a hint of geostatistics. On your right side, I guess, on the lower side, you see a graph, which we call commonly as the semi-variogram. So whenever we are trying to make a map, soil map, a basic soil map, so we use the most commonly used technique is kriging. And the semi-variogram is the heart of kriging, you can say. All information that is used in the kriging model comes from the semi-variogram. So it's very important to understand what this semi-variogram is. Now, if you look at the equation, it is nothing but the variance. Okay, that's why it's called the semi-variogram, because we are using half of the variance. So if we go by the basic definition of variance, it is the difference of a value from the mean divided by the total number of value, and you can square the differences to avoid negative values. So that is actually a variance. In this case, what is happening is, just a sec. Okay. So we have different points here. So this is the soil sample collected from a farm, and we have each sample 120 meters apart. But for the sake of explanation, I'll just say it's 100 meters apart. We have taken all these samples here. So each sample will be having a different value from the other. So that means there'll be some variance between these two differences. So in the semi-variogram, on one side, that is on the y-axis, we are plotting semi-variance, and on the x-axis, we are plotting the distance. So let's say it's like 100, 200. I hope you can see the points I'm making with a red pen here. So 500, 600. So these are the different distance points. So let's say we target this particular point. So this point to this point, supposing the value of organic carbon is 1 here at this point and 0.5. So there is a difference of 0.5. So when we are taking the semi-variogram, we'll say 1 and then 0.5, 1 minus 0.5 squared. So likewise, we take differences from each point at this point. for every one point to another point, and then we sum all of them. This is a summation symbol for all points. And then we get the semi-variance for that particular distance. So that distance, supposing this is 100, and we'll get a specific semi-variance here. But since there are hundreds of points, you'll have numerous points here. So these are then averaged, which is called the process of binning. So what is happening is when we are plotting these variances in distances shape, we'll get a graph something like this. Usually we'll get something like this. Okay. So you see that the semi-variance is increasing as the distance is increasing. That means the points that are closer to one another are more related to one another. Now this forms the basis for soil mapping. That means the point here will be more related to point here than this one. So if you know the concept of correlation, that means if something is increasing, one variable is increasing, the other variable will also increase. So in this is called the process of autocorrelation. That means this point is related with this point is related with this point. So the nearer the point, the more will be relation and lower will be the variance. So as we move on, this line will straighten. That means from at a certain point of distance, this semi-variance will level off. So what it means is that up to a particular distance, one point is influencing the value of other point. Supposing if it is 1, 2, 3, 4, and 5, 500 meters range. So that means this point is influencing the soil value up to 500 meters. So that if this point is having a particular nitrogen value, any value within these 500 meters will be related to this value, and then to this, and then to this, and so on. So this is the process that is called autocorrelation, and this is the technique that is used to map the soil properties in unknown locations. So to better understand this process, we'll just take an example of a farm that we recently mapped. So what are the steps that you need to follow if you want to create a soil map for a farm level soil map? So one of the first steps that you will be doing will be the digitization, and of course field sampling, and then laboratory analysis, and finally the generation of maps by using interpolation techniques like rigging. Okay, so let's start with the digitization process. So now this is the farm map. We obtained this map from the estates division of our university. So we brought it into scanned it first, and then brought it into the ArcGIS software environment. So once we bring a paper map into the GIS environment, it is not having latitudes and longitude. So now what happens is this needs to be given latitude and longitude so that we can work on this. So if you see, this is a scanned map, and scanned map is then given latitude and longitude. Once this scan map is given latitude and longitude, because the earth is round, its shape will be twisted. So then again, it has to be reprojected to a planar form. So this is the final map that has been. Now this map will be used to digitize the boundaries of the farm. So this is basically the first step. Nowadays, most of the boundaries of political boundaries are actually already digitized, so we don't have to do that. But if you are making maps for a specific area of your liking or your choice, or your study area that has not been mapped earlier, you will have to go for the digitization process. We use the on-screen digitization in the ArcMap or QGIS software. Generally, we used to use a lot of ArcGIS earlier, but now you see that the QGIS, another open source and free software. In fact, I would ask all the students who are interested in this, they can freely download the QGIS from the web and can work on these things, and the software is free for everyone. So we can go for digitization. So this is the boundary of the entire form, and this is a rivulet that is flowing through the form. So this is the part of the form that is actually in under agriculture. So what we did was, once the form map was digitized and created, the next step was to have a sampling spot. So we went for grid sampling. This is the best method of sampling if our area is small. So this is around 165 hectares of area, and we created a grid of 120 meter by 120 meter. Now there are two ways of collecting samples by GPS. Here we see that we collected samples very uniformly from one grid to another. So if we're going to field and taking a GPS with you, it'll be very difficult to have a very fine grid like this one. So what we did was we followed a reverse process. That means we created the grid first on the in the software, and then we transferred these points to a GPS. And the GPS usually have a proximity sensor. So whenever we are reaching close to a point from where we have to take sample, it gives out a beep or an alarm. And then we know that we are near that particular place where we're going to take the sample. And then we collected samples. Now, these are around 143 locations, and we collected 286 samples, both from surface and subsurface. Then these were analyzed in the laboratory. I'll not go in detail about that. So this is the data that was finally loaded into the ArcGIS. So you see different properties: clay, sand, bulk density, calcium, potassium, sodium, etc. And on one side, you see the sampling codes and everything and what depth it was taken. So this was all transferred and entered into the GIS environment for each and every point. And once that was done, so there were two strategies that we followed. One was geostatistics, that was kriging, and another one was a simple inverse dating distance weighting technique. So there are two different techniques that are commonly used, but mostly geostatistics is preferred if your data is following normality. So this was done, and these were the final results from these maps. This is a surface map for clay and surface map for sand. So in this, what you see that we have not used any variable other than the soil samples that we have collected. But that's all good because our sampling distance were not very large. So, but when we move from farm level to a district level, or even a level, maybe a province level, so the thing is the number of samples reduces drastically. We cannot collect soil samples for every 120 meters. So our grid will be much larger, we'll be collecting a lot less number of samples. In fact, even if you have the money to collect so many samples from a entire district at 120 meter, you will not have the time to collect. So we have to make a balance between the output quality and the type of sampling that we can do. Of course, the more the number of samples, the better will be the output that is given. But this is not possible at a very large scale. So what do we do then? Because we know the soils are dynamic. They have a lot of variation between them. So for small distances, the variation can follow a particular gradient from one sample to another. But for large distance, that gradient doesn't help because there'll be a lot of variation. Now, this is a sample map that you see on the right is also done by kriging. This is around 165 samples from the entire Jammu district. That was 43 samples from just 165 hectares, and this is 165 samples from just entire, this is around 1,000 square miles. This is around 1,000 square miles. So you can imagine the dearth of soil samples that we have collected here. So if we are going for the same techniques as inverse distance weighting or triggering in this one, so we'll be making a map that is of very little value to anyone. Not even the policy planners would be using it. So what do we do in this case? We cannot collect so many samples from such a large area. Maybe if we work hard, we can go for 500 or 1,000 samples for that. I mean, we should actually go for 500. This is just for the example, I have made a poor quality map using only 165, 170 samples, but like 500 samples is still recommended. Uh, Even for machine learning models also, depending upon the area. So what do we do then? So we go back to soils 101. That is something we teach in the very beginning in the BSc first year about soils. That is the factors that are forming the soil. So you see that everything is dependent on something. The soil types, wherever they have formed, are dependent upon certain factors, which are parent material, relief, time, climate, and organisms. So we have all know this. We've all read about these things. Now, these are the factors that will decide the type of soil at any given place. So these will become our environmental variables whenever we are trying to predict the soil properties. In the earlier version of soil maps where the area was small, we were using simple kriging techniques, but that is not possible here. So we are taking the help of soil forming factors, which will decide the type of soil at any given place. Now in McBrittney in 2003, he modified this model given by Jenny. In fact, Jenny didn't give that model. He just said these are the factors that are affecting the formation of the soils. So what McBrittney improvised upon that because he wanted to make a model which is now commonly called as the Scorpan model. So he added two more points to this. One is the soil attributes. That is the samples I was talking about, the samples that you are taking. And the other one was space because we are going to create maps. So we have to work on a spatial information. So these two things were added by McBrittney. So what are these things? So in this model, he refers to a soil property at any given place as a function of the soil data that we have collected and all the soil forming factors. And then for space, he writes X and Y. And then there's a residual error. Now, this is very important, residual error. So this will decide the accuracy of your predictions or the mapping quality, what we can say. So the lower the error, the better will be the prediction. So this is the Scorpion model. So he said the soil at any given place is a function of this. And this Scorpion model can be used for quantitative prediction of soil classes or continuous soil attribute, both based upon the empirical observation that we have been taking. So now let's see each of these factors separately. So one thing that is available with us is the legacy soil data. Now, if you go through different departments of soil science in ICR institutions, university, you'll see that there's a lot of soil information that is already collected by the different, you can say, scientists or the scientific fraternity. A lot of data is already available. So that is called the legacy soil data, which has already been standardized and known to be. However, there are certain problems with the legacy data because different, what we call different methodologies might have been adopted to analyze that particular data, and different type of sampling approach could have been followed. So that thing we have to take care, which is called the harmonization of data. This is very important for the purpose of model calibration. It will also reduce the time that you have already spent on that you would spend on soil sampling. But it's not that you can completely leave out the soil sampling process, even if you have some old data with you, because a fresh data is also required to enhance your database. So, but this helps in reducing the sampling cost and helps in model calibration. And this forms the core of the prediction model that you will be generating. Apart from that, then next step would be to go for soil sampling. Before we start with soil sampling process, it's very important to see what type of area that you are targeting. For example, if I talk about, I've shown you the Jammu district map. Usually I show this as an example because half of this area is plain and the other half is hilly. So there'll be a lot of difference in how the environmental variables behave in this area, because one part is totally plain and the other part is hilly. One part is irrigated, other one is rain-fed. There's agriculture in one area. There are dry zones, and there is a lot of vegetation in other area. So it's a very good example area where we can test all these different types of models and test their accuracy against the other. So when we start or go for soil sampling, then we have to be very careful that how we are sampling. We cannot leave out the zones completely. It has to be a very representative type of sampling, something we call the strategic random sampling. Now, random because we have to collect samples randomly, we can generate points randomly, but strategic because we'll maybe making out certain uh, what we call designating certain areas beforehand so that we don't miss out a specific type of a landscape, or we don't miss out a specific type of vegetation. For example, if when we are talking about the Jammu district, so we know that we have to collect the samples from the plains and then we have to collect the samples from hills. So that is two zones. And then we have to collect the samples from the dry areas, then we have to collect the samples from the irrigated areas. So those are another two. So we have to see that the samples are distributed evenly, but within the zones, we are free to collect the samples randomly to avoid statistical bias. So that is very important. And then again, the more recent techniques also start using models, not just for making maps, but also for collecting samples beforehand. We have not done it ourselves here right now, but in our next step, we'll be using a few of the machine learning models simply to collect the soil samples from any given area. So once your samples are collected, we analyze them with the standard procedures or whatever the procedures that have been standardized by your area. Now, once this soil data is collected, the next step will be to collect the environmental variables. So now this is the climate, organisms, biosphere, relief, and parent material. So when it comes to climate, we have a lot of information about climate over a given area. Now, what's important here is that why these variables are now being used so commonly is because we have having access to remote sensing data. And the good thing about remote sensing data is that it is continuous for the entire given area. Or for example, if you see the red outline here, of a particular district in J&K. So you see that what is there? It's a continuous data. You see the landforms, you see the vegetation types. Now, this is the continuity of data that will help us in making the prediction models and predicting soil properties for the entire district based upon a few sample points that we have collected. So you can collect the different type of data. For example, if there's a lot of climatic variation in your region, your study area, then this becomes very important. But if it is a smaller area or a single district where there's not a lot of variation in the climate, then we can skip this as an environmental variable. However, the biosphere or vegetation is very critical as an environmental covariate. Now, this vegetation data can be obtained from remote sensing. We have Indian resource satellites like the resource set 2, which is having a linear imaging and scanning sensor that collects the information about vegetation. And this can be used to identify the land use, land cover, our distances. But it's not like we are only okay, we have got this land use, land cover, we have got this remote sensing data, and then we make a land use map and then it's done. But instead of that, we are calculating numerous uh, what we call numerous indices that will be relating with the soil samples that we have collected. For example, the most common indices is the normalized difference vegetation index, commonly called as the NDVI. Similar to this, there are many other indices that can be calculated from these remote sensing imageries, like the brightness index, soil adjusted vegetation index, ratio vegetation, and there's a numerous list. I'll show you in one of my slides when we move ahead. So this is one of the environmental covariates that we can generate from this. And then another important property is the topography. Now, when I was talking about the Jammu district, I told you some area is plain, some is hilly. So there'll be a lot of difference in the topography. And that means there'll be a lot of difference in the soil types as well. So we can have this topography data from the remote sensing imageries. If you want to use the Indian data, it is available from Cartosat. We can also download the data from Esther, which is about 28 point some, near about 30 meters resolution, you can say. So once again, if we are having the topographic data, it doesn't mean that we'll just be having the elevation values only. So we'll be calculating a number of indices from the topographic data also. And some of the indices will be affecting your models more as compared to others. But the more the indices you have, better will be the, you can say, the quality of the model that will be generating. And then coming to parent material, okay, if it's a smaller area, it will be more or less a similar parent material. But if you are dealing with a very large area, I suggest that you should have geology maps of that particular region, and the data from that maps can be utilized as one of the covariates in this. Okay, this is a list of, on the left hand, we have a list of different indices that are related with vegetation and soils, like brightness index, greenness. So this indices is like a permutation and combination arithmetically of different bands that are available in the satellite data. On the right side, we have the different topographic indices like steepness, elevation data, plan curvature, mean curvature, what is the flow direction, and wetness index, and so on and so forth. So all these can be easily created in QGIS software. You just need to download imageries, which are also freely available for most of the high resolutions from 20 meters, 30 meters. This is commonly and freely available from Landsat and Sentinel, and topographic one is available from Aster and Cartosat. Okay, now once we have all these maps for individual indices that are derived from the remote sensing images, the next step will be to look for what type of models we need to use. So nowadays, machine learning models are being put to use, and their use have increased in the last 5 years. These are random forest is pretty common. It is, if you go through certain recent publications, you'll see that the most commonly used machine learning algorithm is the random forest, not only in soil mapping, but in many other prediction models that are not related with soils, but are related with other natural resources. Apart from that, we have sport vector machine, XGBoost, QBIS, and many other models are coming. But the most commonly used is a random forest, and we'll try to stay focused on that for the sake of this presentation. Okay, so now you have collected the soil data. We have different points from different a particular given area, and then and below here you see that you have collected the covariates. These are the different indices that you have derived from the remote sensing imagery. And you see that these indices have a continuous data, while this is only a point data at specific points. So this is one point, this is the other point, 1 point here, 1 point here, 1 point here. Supposing we are talking about organic carbon, so these all data points will be having the organic carbon values. But the thing is that we have to populate this area where we have no data at all. This area will be populating. And these are the covariates that will be helping us to populate this area. Now, what we do is we run the, for example, we are running the random forest models. So what we'll be doing first, we'll be extracting the value of each covariate for each of these points for that particular location. So for example, if you have 30 covariates, so we have 30 values for that. So in a table. So for each point of OC at a particular location, we extract the particular value of each of the environmental covariates. For example, if we are extracting for NDVI. So NDVI value corresponding to this organic carbon value. A ratio vegetation value corresponding to this particular organic carbon value. So we have organic carbon value that is related to each of the indices. Like we have 30, 40 indices. So we have values for all the 40 indices and the corresponding organic carbon value. So what we are doing that we are plucking out all the indices values here so that we know what are the factors that are influencing the organic carbon at any particular given location. So when we have hundreds of such values, supposing 500 points, so 500 points we have, then we are good to make a particular model or run a model. So we run the random forest model and predict an equation. So it will give us a prediction model for that particular area. And then we can test that model and create a soil map, plus also work out the errors. Now, working out errors is very important so that we know that what we have made is an accurate map. So this is your, from one of our studies. So this is your XY locations, X and Y locations, latitude and longitude. This is your soil organic carbon data from that particular location, and these are the extracted values of different indices. So this continues for up to 32 variables because I've used 32 different covariates to predict this set. Okay. Now, when we talk about random forest, so this is like a tree-based system. So with that, decisions by the model are based upon the trees. So I've given you a simple example here. So we're talking about a food box here, and we are deciding what that food box is containing. So, for example, if the diameter is more than 2, if it is less than 2, it's a cherry. If it is more than 2, it's an apple. So this is one tree. Now, from that tree, whether the color is orange or not. So between apple and orange, it can decide this is apple. If the color is not orange, if the color is orange, then they are of course oranges. Then of course there are different combinations. So we will not be sticking to just one tree type, but there'll be combination of different trees, some starting with the other. So here we are starting with diameter, then moving down. Here we are starting with color and then moving down. Here we are starting with a different diameter value. Here we have taken 2. Here we are taking 1. Then we can say if it is a small circle or a big circle, and so on and so forth. So these trees will actually decide. So in this case, we are like having 32 variables that are deciding the organic carbon at any given location. So we'll be testing hundreds of trees in this. So this is a number of trees on one side, and on the y-axis you have error. The more the number of trees, prediction trees that we are using, the lower will be the error. So commonly we use 500 trees. So you see that the error kind of decreases If that is not happening, then of course there will be something wrong with that. So commonly we use 500 trees while calculating, while what we call while making the prediction model for that particular area. So once this is done, then another output that your model will also give is that which is the most what we called what we can say, which covariate, environmental covariate that we have derived from remote sensing imagery is the one that is contributing the most to the model. So this is like showing vegetation index, NDVI is on top, NDVA, but it's not necessarily the same one will be on top. Sometimes we have topographic models, like in one of the uh, uh, our for soil properties, we have received that topography is making a lot of difference as compared to vegetation models. So it will depend upon what factors are affecting the distribution of that particular soil property. Okay, now this is another flow chart like what we have. So we are downloading like it's like a summary of what we have just told you. So we are downloading data from the remote satellites, and then we have the soil samples that are collected and analyzed for soil organic carbon. We combine both the data points. Then that data is actually split. I mean, when we are running a model, prediction model like random forest, so what we'll do, we'll split the data into two parts. So supposing 70% of the data will be used from training the data sets, and this data 70% will be used for training the data set. The other 30% will be kept for validation. So once we have trained the data set using the 70% data, and we have made the machine learning model and prediction model, then what we are doing is, then we are making the prediction maps here. And once these prediction maps are generated based on this 70% data, then we use the validation data, that is the 30% data, to actually verify what or how accurate our results are. So commonly used error indicators are like R-square value and the root mean square error. Okay, so what is happening here is that we have extracted, we have made the final map, and we have kept 30% of the points. So now we see that this is the actual point at a particular place and an actual carbon value, supposing. So we match it with the maps that we have created and see what was the value that was predicted. So we plot predicted values and observed values. So we'll get certain points here, here, and then we can get an R-square value from this, how the observed and the predicted values behave. The more the R-square, better is your map. But also important is the root mean square error. The lower the error, the better will be your map. So these are some of the maps that have been created. Let's focus on this one that is made by Random Forest and this one that is made by Kriging. So you see the quality of these two maps. So this is having much more and much higher information as compared to this one. I'll show you another map where okay, so this is once again the map of the Jammu district for organic carbon. Here you see that we have done it by simply only by Kriging. This is from about 200 sample points, the organic carbon, and you see large blocks of similar color. We have less than 0.5, we have less than 0.5 to 0.6, 0.6 to 0.7. So different organic carbon content zones are made here. Now you compare this with the model, random machine learning model, and you see that there's a lot of variation between these two models. So this is simply based on autocorrelation by using 200 points. The same 200 points have been used here in the random forest model, but the clarity and accuracy of this model in one look, especially to me, of course, it may not be to you because I've been working in this area, I can really make out that this is much more accurate because this is really defined by the type of vegetation. We have forest here, so we have a high organic carbon here. Here, high organic carbon here. Very low here because this is our dry zone. This is irrigated zone. Once again, higher organic carbon, but lower than the forest areas. But in this case, we see that there is a lot of vegetation here, but we have a different sort of classification because the 200 samples is not good enough for the entire area when it comes to kriging, but it behaves very good when we use a machine learning model, because machine learning model here is using the environmental covariates to predict the soil properties. That's why the accuracy has increased. Now let's not go by just by this on the visual way about the accuracy. We had one small watershed in this particular area here. It could be just as small as this one. So this is just 400 hectares. There'll be somewhere here, probably, yeah, somewhere here in this one. So let's see if it is in kriging and we want to see what is the distribution in that particular watershed. You will just receive one single color. That means the values between 0.75 and 1. But let's see how our random forest did. Okay. So this is that particular watershed that I was talking about. And this watershed is created by using 85 different soil sampling points. This map is created. But what we were getting from this one, we were getting only one single value, 0.75 and 1. So, but if we see closely in the watershed, this is 0.5, this is 0.5 to 0.75. So there's a lot of variation. Very low here, high here, because here we have forest, here we have dry farming. Okay. Now let's see how random forest did with the same number of samples what we have done with kriging. So this is the map here. So this is the values from the random forest. So you see less than 6. So this is less than 0.5. This is the dry area which is having low organic carbon. So this one. And this is 0.75 to 1, and this is 0.72, and this is more than 1. So this falls somewhere here, these 2 points. So you can see that not even 1 point was used from this watershed to create the random forest. And you can see how accurate it is. Now this is just done by 200 points to test the accuracy of the models. When we are going to increase the number of points for the entire district, we'll see that the quality of the map will improve still further. This is also some points using different models. This is using sport vector machine. This is the random forest. This is the XGBoost. This is for another watershed that we have studied. Now these differences can be we can study the accuracy of these different models by using root mean square error. So the lowest is for the random forest. Sometimes it could be for sport vector machine also, or some XGBoost also. QBIS, depending upon the type of sampling and the type of area that you're studying. And the R square value is also very high. So this is the model for choice for most of the studies. So talking about this, that I see that there are a lot of opportunities. So it's very difficult to cover such a vast topic in a single lecture, but I hope that you might have got some something out of it. So available soil data is increasing numerically, and we are having a lot of tools nowadays. And the amazing thing is that a lot of these tools are free, like QGIS is there. I have used R Studio to make these maps, which is also free. It needs a little bit knowledge about coding, but that is something everybody and all of us who are working in agriculture should start learning, especially the students. I suggest that they should take up somewhat classes about coding, maybe Python or R. Then we have different soil data models that fit for different locations, different land uses and land areas, then increasing soil data harmonization. So we have come to a stage where most of our soil methodologies have been standardized, and most of the areas are using similar models, similar methods. Then again, the spatial infrastructures are growing. We are having a lot of remote sensing data, which we were not having earlier. The resolution of that remote sensing data has increased. We have global coverage of the digital elevation models. We have web servers that are totally dedicated to providing you the remote sensing imageries and other sort of data like Landsat and Sentinel and so on. And then we have methods, we have geostatistics, we have data mining methods, we have expert knowledge modeling, and the scope of digital soil mapping is increasing day by day. And I would like to tell you this here that we now have got a 5-year project in where we are going to make one of its kind land information system for Jammu and Kashmir. So both our universities in Kashmir and Jammu are working together to bring out a J&K land soil and land information system, because it's become much easier after using the machine learning models. You know that J&K is largely a mountainous region. Collection of soil samples and accessibility is very poor. We cannot collect large number of samples, so it was a you can say a non-starter sort of. We had very limited information, but with the advent of machine learning and the availability of a very high resolution remote sensing data, we are now in a position to get a very high quality maps of soils in for this region. So in the end, I would like to say that our advances in computing technology with the availability of remote sensing data and spatial information has greatly facilitated the development of DSMs, that is the digital soil map. And these techniques have greatly reduced the cost and time required for producing detailed and more accurate soil maps. So thank you very much. And before I leave, I would like to say that digital soil maps, they are really pretty. When you look at the random forest map that I had made, it looks really good. But be very aware that if you're making a wrong map, it will look very good because there are a lot of colors in it, but it'll be of very little use. And in fact, it will be what we say, it's better not to have any map than to have a wrong map. So you have to be very careful with that. So residuals, errors, R-square, these things become very important when you make a soil map using digital soil mapping. So thank you very much. And I hope I am right on time.
जी सर, लेकिन 10 मिनट का सर अपन डाउट क्लियरिंग सेशन रखेंगे सर.
Yeah, sure.
जी रोहित जी, चैट बॉक्स ऑन करिए. आप चैट बॉक्स को ऑन कर दीजिए. जो पार्टिसिपेंट्स अपनी क्वेरी रेज करना चाहते हैं, जिनको कोई डाउट है, वो डॉक्टर साहब से पूछ सकते हैं डायरेक्टली चैट बॉक्स में. रोहित जी, मेरी आवाज आ रही है आपको?
यस सर.
हाँ, चैट बॉक्स को ऑन कर दिया आपने?
कर दिया सर.
ठीक है. पहली तो क्वेरी है सर कि प्लीज सेंड पीपीटी. ठीक है, हम डॉक्टर साहब से अनुरोध करेंगे कि वो पीपीटी दे दें.
नहीं, डेफिनेटली.
ठीक है. दूसरी बात है कि हाउ टू लर्न जीआईएस.
ओके, कहाँ पे है?
हाँ, इसी पे चैट बॉक्स में. हाँ.
I started with an introduction to GIS only, but of course it'll take some time. I mean, it's not like you learn it in a day. There's no better place to start than YouTube. If you want to learn it on your own, then there are a lot of videos about GIS on YouTube, or you can join a course. But what is important here is whatever you do hands-on. Because if you go just for theoretical stuff, you'll never be able to learn these, whether it be GIS or remote sensory imagery management. So whatever you do, and you do hands-on training. If you don't have access to any specialized training in your area, then I'll suggest that you go for YouTube. But what is important here is that you search first that what is need to be done. What are the steps that you need to take in learning GIS, from where to start. Start with the very basics introduction, like from digitization. You can start from digitization. You can start for creating points in ArcGIS, then creating lines in, then creating polygons. There'll be a lot of steps here. And if you guys are well versed with the chat GPT nowadays, you can simply write what are the steps that I should do to learn GIS. It'll give you a 8 to 10 different splits of the how you can learn GIS. So starting from first point. So that's how, I mean, you can learn. There are long courses also. There are diplomas also. There are programs from Indian IRS also, Dehradun. But I think if you have time on your own and you can do it, you can learn on the YouTube itself. There are so many lectures and so many things. You start with the very basics, and then you have to, one thing is important, that you have to do it yourself, hands-on. So you can download QGIS on your laptop, and then you can start from the basics.
Sir, एक question है. Why soil forming factors called active and passive factors?
Oh, that is very simple, because if someone is actively contributing to a certain thing, and जैसे कुछ बच्चे होते हैं active होते हैं, कुछ passive type के होते हैं, so like some of the factors like climate is an active factor because it's directly influencing the soil formation process. But जो passive factors होते हैं, they are just there. जैसे time हो गया, time निकल रहा है, it is not directly, but क्योंकि time निकलते जा रहा है, तो आपका जो changes हैं वो होते जा रही हैं. It is not directly influencing that. So that is the basic, it's the definition as in the dictionary, you can say.
जी, एक question है sir, how can we create a shape file using lat and long?
Okay, shape file using lat and long. Achha, okay, you might be having points of latitude and longitude. I guess that's what he means by this. So if it is in an Excel file, supposing you have a Excel or CSV file where we have one column of lat and one column of longitudes. So what we do is we can import this file into a GIS software, could be ArcGIS or could be QGIS, and then once it is imported, you can right click on this file and use a function called add XY points. So you give XY to lat and long, and it will be displayed as a shapefile in the GIS environment.
बहुत बढ़िया.
Of course, you'll have to save it to a shapefile afterwards once it's created.
Next है sir कि this presentation is very excellent. Sir, how many soil samples required to do 1 hectare land soil maps and the necessary inputs to generate that field soil maps?
Okay, 1 hectare soil map. I will not recommend you go for mapping of 1 hectare soil map because it's not a very big area. You can just collect a few samples for a 1 hectare land area. So for mapping is usually done for a bigger areas. For 1 hectare, it's not really a big area. It's like just 2.5 acres of land. Even if you collect a 5 to 10 samples, like 10, 15 samples, that will be enough to give you an idea of that particular field. But usually the maps are required for bigger areas, like 100 hectares land, 50 hectares. So for 1 hectare, I have not done mapping, but it can, but I have done a spatial variability studies for smaller areas, but that was just to not actually make maps for that particular area, but for understanding the variations or what we call the pedometrics or residual errors, how variable the soil could be in a small area. That was done during my postdoc. But of course, the smaller the area, you have the liberty to have a smaller distances. That means you have the time. For example, you can have like 10 meters, 20 meters distance from one sample to another sample, so that you can collect more number of samples from that particular field. But my recommendation is that we don't usually make maps for 1 hectare. So it'll be bigger forms that we go for.
जी सर, ज्यादातर तारीफें हुई हैं सर कि नाइस प्रेजेंटेशन, प्लीज शेयर
Thank you so much. Yeah, I'll share that. Yeah.
जी सर, एक स्टूडेंट का क्वेश्चन है कि व्हाट टेक्निकल स्किल्स रिक्वायर्ड फॉर एग्रीकल्चर ग्रेजुएट्स एंड व्हाट्स योर सजेशंस फॉर यंग एग्री ग्रेजुएट्स?
Okay, I did say that at the end that I want all the young agri graduates to learn some amount of coding, whether he's a soil scientist or he's following any other field, agronomy or whatever. Some sort of coding and computer skills are must. Now, basic computer skills is like we know how to use Word for typing and printing. We have to move beyond that. Okay, you have to use these things for other purposes also. Excel, you can do so much on Excel. But apart from that, I want that each of the graduates should at least go for at least learning one language, and it doesn't take time. If I can do at this age, learn R to make these maps, and I think there's a lot of scope for everyone. And my recommendation is that Python will be the #1 choice that you should go, because even if you are going outside India, they will definitely be happy if you are having an additional knowledge of any coding, because of a lot of work on pedometrics and modeling is going on around the world. So coding, #1, Python. You can also learn R because they are going towards open source softwares. And then of course, database management, because they are generating lots and lots of data nowadays. So apart from your own subject, you should also go and try to integrate these languages in your subject form. So that is one of the biggest takes from my recent visit to the US, that they are generating a lot of data, and all the graduates, PhD students, they are having some sort of skill related with computers, especially small coding, so that they can make their own models and run their own models. That is the basic idea in this one. So that is the #1 suggestion for all the graduate students.
जी, महिमा जी, महिमा दीक्षित.
Yes, sir.
जी.
Sir, we are very thankful to you for giving us such nice lecture. It was very informative. In fact, I feel that GIS and RS is very mandatory these days in case of soil mapping and all. And if we have good roots and good command over this particular arena, we will flourish like anything. Thank you so much, sir. The presentation was very informative, sir. It was very nice. The research studies were very commendable, sir. Thank you so much for sharing this vast knowledge with us. It was very inspiring, sir, to have you with us.
Okay. Thank you so much for the opportunity. And I see a lot of people actually asking questions, and that's a very good thing. Mostly what happens is you just give presentation and there are no questions and there's no interaction. So this was great. I mean, there's a lot of, there's a big and diverse group. I thank Dr. Ankur and Mahima for the opportunity and connecting this wonderful program. Thank you very much.
Thank you.
बहुत बहुत धन्यवाद सर, मेरे आह्वान पर आपने ज्वाइन किया. बहुत बहुत धन्यवाद सभी पार्टिसिपेंट्स.
मैं आपको प्रेजेंटेशन शेयर कर दूंगा.
मैं अपनी ईमेल आईडी भेज दूंगा सर, ऑफिस वाली, आप उस पर भेज देना प्लीज.
राइट.
ठीक. थैंक यू सर.
Okay, sir. Thank you, sir. Good evening, sir.